Hello, students. This is Mr. Allen, and today we're going to move forward to section 5.2, which is on growth and decay. Our objectives here are to use separation of variable to solve simple differential equations and to use exponential functions to model growth and decay in applied problems. We have learned to analyze the solutions visually of differential equations using slope fields and other methods, including Euler's method, but I've kind of removed that from our content for this year due to the limited amount of time we have. Analytically, you've learned to solve only two types of differential equations. That is y prime equals f of x and y double prime equals f of x. In this section, you're going to learn how to solve more general types of differential equations. The strategy is to rewrite the equation so that each variable only occurs once on each side of the equation. This is called separation of variables. So consider the following differential equation: y prime equals 2x over y. We can see here that we have variables y on both sides of this equation. The first thing that we want to do is try to get everything in terms of x on one side and everything in terms of y on the other side. So we can multiply both sides by y. Now, it might appear that the only variable x that we have right now is on the right-hand side. That actually isn't quite the case. That y prime has an x embedded in it. So what we're going to do is we're going to take the y prime and think of that as a dy over dx. So this integral, we're undoing differentiation, is going to be y, or the integral of y dy equals the integral of 2x dx. Integrate the left-hand side using our power rule. We're going to get 1/2 y squared equals, and then the right-hand side is going to be x squared plus c sub 1. So that's the first constant. We're using the power rule here. So this is hopefully a pretty easy integral to understand. Now, too far. We can go ahead and we can multiply through by 2, and we'll get y squared minus 2x squared equals c. So the general solution is y squared minus 2x squared equals c. Notice that when you integrate both sides of the equation in this example, you do not need to add a constant of integration to both sides. When you do, you'll still get the same result. So if I go back to that original equation the original integral equation in the previous slide, you will get the following. This is the original integral equation. When you integrate both sides, you're going to get 1/2 y squared plus c2 equals, and then on the right-hand side, you'll get x squared plus c3. But whenever you take c2 minus c, or c3 minus c2, you'll just essentially get c1. And I should probably note this now. C is any real number, is equivalent to 2c, is equivalent to c plus 1, is equivalent to c divided by 3. So anytime there's a c, you can just reduce that to just c. Some people prefer to use the Leibniz notation of differential equations. In fact, this is what you'll see me do in class. Instead of writing y prime, you'll see me write dy over dx. And it just makes the separation of variable a little bit, I think, easier to make sure that you got all the y's on one side and all the x's on the other. So instead of writing our equation, remember the original equation was y prime equals 2x over y. I would write that as dy over dx equals 2x over y. Now we'll just cross multiply here and we'll get y dy equals 2x dx integral. You get the same answer. I think this is probably my preferred method, is the Leibniz notation. By the way, he and Newton are the guys that created calculus. All right, so let's talk about growth and decay models. In many applications, the rate of change of a variable y is proportional to the value of y. If y is a function of time t, the proportion can be written as follows: dy is to dt is ky. So we have a derivative on the left. We have an equal sign. This is a differential equation. And I'm going to show you the solution to this particular differential equation. And again, this is a directly proportional model. Hopefully you remember that we did direct proportions and inverse, etc. The general solution for the differential equation is given by the following. So this is probably the most important slide for all of our growth and decay problems. If you have the following differential equation, which is what we just saw on this last slide here, y prime equals ky. Notice that k, by the way, is a constant. The solution is y equals ce to the kt. Now, I'll show you the derivation of that formula in class, but this is the solution. So this is the general solution for that differential equation, where c is the initial value, and this is the proportionality constant k, and it is exponential growth when k is greater than 0 and decay when it's less than 0. Please, 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 I shouldn't even say please, I hope you guys covered this last year in pre-calculus, maybe even in algebra 2. I hope that equation looks familiar. So let's see an example of that. So it says the rate of change of y is proportional, directly proportional to y. When t is equal to 0, y is equal to 2. When t is equal to 2, y is equal to 4. What is the value of y when t is equal to 3? So they've given us quite a bit of information here, but it still is like, what the heck are we doing here? So since it tells us that this rate of change is proportional, we know we're dealing with this differential equation. And by this theorem on the previous slide, theorem 5.1, we know that this is the solution for that differential equation. So now what we can do is we can just start substituting values in. So let's go ahead and figure out what C is based on C and K. We're going to find C first. So we're going to use this first piece of information. When T is 0, Y is 2. So I'll put 0 in for T and 2 in for Y. Therefore, C has to be equal to 2. Now, we've got C is equal to 2. Now I'm going to use the second bit of information, that's this part right here, T equals 2, Y is equal to 4, and I'm going to plug that in to our equation. Remember, our equation was Y equals, and we found C was 2 already, right? And this is KT. So now what we're doing was we're plugging the 4 in for the Y, and we're going to plug 2 in for the T. That gives us K is equal to 1/2 ln of 2, which is approximately 0.3466. So the model is Y equals 2e to the 0.3466 t. Now, I will let you know that in most applied problems, you do not want to round. So honestly, I would probably write this as y equals 2e to the ln of the square root of 2 times t. This is your k value. This k value we established right there. All right, and in fact, let me go ahead and erase this here now that I kind of should have written that maybe in a better place. We'll get rid of it. Okay. So this curve, this dark curve, I'll do it in purple. This curve right here, this is the curve that is generated by this function. You will see that it goes through the point 0.2, which was our first initial condition. It also goes through the point 2,4. So now we can use it to figure out what the value is when t is equal to 3. What does y equal? Well, now we can just use our curve here, and we will see that it is about 5.657. Radioactive decay. So what happens is if you have some sort of radioactive material, radioactive isotope, what happens is it's literally decaying. So as it's there, it's literally breaking down. And the half-life is the amount of time it takes for half of it to break down. So for example, if you have 100 pounds of, let's say, carbon, okay, it takes 5,715 years for it to become, if it's 100 pounds now, it would take 5,715 years to become 50 pounds. That's its half-life. That's how long it takes to become half of what it is. And as you can see, uranium, look at the half-life of that, 4 billion years. But then we look at something like Einsteinium, it only takes 276 days to become half. And Nobelium, if I'm saying that correctly, only takes 25 seconds. So this is kind of interesting. So let's look at our final example here. It says we have 10 grams of plutonium. So we're talking about plutonium. Let's go ahead and look back here at the previous slide. So plutonium, that was the second one here. We have 10 grams of plutonium, and it's released in a nuclear accident. How long will it take the 10 grams to decay to 1 gram? So this is going to be modeled by the differential equation. In fact, let me just say this. Y prime equals ky, which we know the solution to that, which is y equals c e to the kt, which is basically what I've already typed here. So now let's go ahead and find our values for C and K. So we know that at time t equals 0, there are 10 grams. So if we plug that into our equation, we get the following. We find that C is equal to 10. Great. So that changes our equation. Our equation now is y equals 10e to the kt. We now want to find what k is. So now we're going to use the next fact that we know, and we know that it takes 24,100 years for it to half be gone. So if we have 10 now, after that amount of time, 2,000 or 24,100 years, we will be down to 5. And so that's going to help us figure out what k is. K here turns out to be 1 over 24,100 ln of 1/2. Again, I would store that value right here in my calculator. You notice that it's negative, and the reason it's negative is because it's decaying. This gives us the model that we need. And now the question is, how long is it going to take that 10 grams to become 1 gram? So we're just going to take y to be equal 1. So we need to solve this exponential equation. This is a pre-calculus question now. You're going to divide by 10 on both sides, then do the log on both sides, etc., and you will get the answer of 80,059 years. It's a long time. All right, that's it, guys. Thank you for your attention.